Hello. Your computer files are very safe. Or are they? Let's talk about encryption. Almost all methods of classical encryption work through mapping one letter of the alphabet to another. The result is a message of gibberish that can only be translated back into the original message if the receiver knows the decryption key. This is one of the simplest examples. It takes the alphabet and maps it to a version of the alphabet where every letter has been shifted 3 places. This is the key to the cipher. The main disadvantage of classical encryption is that once the encryption method has been established, there is no way of knowing whether or not someone has intercepted the key to your cipher, and therefore not knowing if your code has been broken. Modern internet encryption methods have come a long way since then. PGP is a modern encryption tool. To use PGP, users generate a public-private key pair. They share their public key and encrypt messages with others' public keys and decrypt messages only with their private key. While highly secure and widely used for email and file encryption, its setup can be complex and relies on securely managing keys and verifying their authenticity. PGP encryption is also vulnerable to future quantum computing attacks. These are all powerful computers currently in development that would be able to break almost all forms of modern encryption. This is where quantum cryptography comes in. Quantum mechanics may seem like a daunting and confusing topic. In reality, all quantum means is a discrete quantity of energy, like a packet. It arose from the discovery that light behaves like a particle as well as a wave as we classically understand it to. These light particles are called photons. The 3 main principles of quantum mechanics that are essential to understanding quantum cryptography are superposition. This means that particles can exist in more than one position or state at a time. This is crucial because it allows the qubits, which are quantum bits, to represent 2 states simultaneously that will collapse into one exact state when observed. This ties into the observer effect. This states that when a quantum state is observed, the state itself is altered. This is important because it makes it possible to know whether or not someone has intercepted your message. Eavesdropping is not passive with quantum cryptography. And finally, no cloning. This is important because it makes it impossible for an eavesdropper to create an exact copy of a quantum cryptographic key. This is important as regular digital data can be copied, making it less secure. Let's take a look at an example of a quantum cryptographic protocol. The BB84 protocol, introduced by Charles Bennett and Giles Brazard in 1984, leverages the fundamental principles of quantum mechanics discussed previously to ensure secure communication. Alice and Bob wish to communicate with each other. Alice first starts by sending Bob a key through a stream of photons. These photons are first polarized by Alice into a certain state, either horizontal, vertical, right diagonal, or left diagonal. Bob is unaware of the correct polarization, so he randomly uses one of 2 beam splitters, which read each photon's polarization. Alice and Bob then compare which splitter they used. The photons observed with the incorrect splitter are discarded, and the remaining sequence of photons is the key. If an eavesdropper attempts to intercept and observe the photons with their own splitters, not only would they not be able to compare the splitters with Alice, they would also change the photon states that Alice and Bob would expect to see through the observer effect. This would blow their cover. In an age where digital security is paramount, quantum cryptography is set to revolutionize how we protect sensitive information. This technology has real-world applications across numerous industries. Banks can use quantum cryptography to secure financial transactions against potential cyber attacks. In healthcare, it safeguards patients' data, ensuring privacy in a world of increasing digital records. Governments can protect classified information, maintaining national security even as quantum computers threaten traditional encryption. With the rise of the internet, quantum cryptography can fortify the security of smart devices, preventing unauthorized access to personal and corporate networks. On a global scale, quantum-secured communication networks are already being tested, paving the way for secure international communications and diplomacy in the future. Quantum cryptography isn't just a technological marvel, it's a critical defense in an increasingly digital world, protecting the data that powers our lives.